What is up, you guys? Welcome to the first lecture on machine learning with TensorFlow and Scikit-learn. So the first lecture is going to serve as an intro to what machine learning is. So I'll keep it really simple for now and try to simplify this term. So when most people hear machine learning, they picture a robot or some sort of deadly, machine working to do repetitive tasks and so forth. But really, machine learning is not just a fantasy, it's already here. As a matter of fact, it has been around for decades in some specialized applications, such as OCR, that is optical character recognition. But the first machine learning application that really became mainstream, which took over the world back in the 1990s, it was the spam filter. Yes, a filter that just removes or rejects email that looks like or is actually spam, right? And then it was followed by hundreds of applications that now quietly power hundreds of products and features that you use on a regular basis, such as online shopping, your daily Google search, voice recognition, natural language processing, handwriting recognition, and many other cool applications. Now, where does machine learning start and where does it end? What exactly does it mean for a machine to learn something? So if I go ahead and download a copy of Wikipedia, has my computer really learned the article within Wikipedia? Does it suddenly become smarter? We will try to address all these questions in this and the coming few lectures that serve as intro to machine learning. So what is machine learning? Now, machine learning is the science of programming computers so that they learn from data. And notice how I wrote from data in red, as this is a very important keyword over here. Data. Now, many other well-known machine learning scientists and computer scientists as well have had their slightly more general definition. For example, Arthur Samuel defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. So, if you were able to teach a computer without, explicitly writing down the if-else statements, the for loops, and so forth, then you have done some sophisticated or maybe naive machine learning. Then we say that the machine has learned. And a more engineering-oriented one, which was defined by Tom Mitchell in 1997, is that a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Now this sounds really philosophical, but it's really not that complicated. But actually, imagine that I have a computer over here. Let's say this thing is a computer, right? And this computer is learning from some experience E given some task, call it T. And there's a certain, performance measure, maybe mean square error or some bit error rate or whatever it may be. It's a criterion that judges the goodness of the model. Now, we say that a computer learns from experience E if its performance on T, as measured by P, of course, improves with E. So the more experience I give the computer, the better it should do with respect to P. Okay? Now, an example here, as we mentioned, is the spam filter. The spam filter is a machine learning program that can learn to flag spam given examples of spam emails. So the data I kick in the computer to teach it are already understood by human beings that they're actually spam. They're labeled by spam, right? And of course, you're going to give the computer other emails such as non-spam emails so that the computer could segregate or distinguish between spam and non-spam. And the examples or data that the system uses to learn are called the training set. They give the computer some training set labeled by spam and not spam, and each training example is called a training instance or sample. In this case, the task T is to flag spams. So that's what we would desire this computer to learn, right? However, E, the experience E, is the training data. right? So you're teaching the computer through examples, right? You're giving it spam and not spam as experience so that it's more experienced and hence to be capable of performing task T in a better way. So what is P over here? You could decide P to be, I don't know, maybe the ratio of correctly classified emails. So the total number of emails, right, with respect to the number of correctly classified email, right? This particular performance measure is called accuracy. It has a name and is often used in classification tasks. So as we will see in the coming lectures. So if you just download a copy of Wikipedia, your computer has a lot more data, but it is not suddenly better at any task, right? You're just stacking in a bunch of data. What is the task to perform? You didn't define it. So to properly teach the computer or the machine, you have to define two main terms over here: the experience, the task, and finally a criterion, E, which is the performance measure, that we can assess the goodness of performance. Now, a natural question over here would be, why would I be interested in a field such as machine learning? Well, let's first go back to the spam filter example and see how it would look like if machine learning doesn't exist. That is, a classical approach of solving the problem would be, first, you'd want to study the problem, right? So you might notice that some words or phrases such as for you, I don't know, something like that, or loan, right? Who on earth would want to send an email with loan, right? I mean, if you want a loan, you just go to the bank. Or you just want $1 million. So 6 zeros. What else? Say, I don't know, like free gift and many others. So let's say you study the problem and you notice that most of spamming emails contain these keywords, right? Or even phrases. And perhaps you would also notice a few other patterns in the sender's name, such as an email that consists of, I don't know, a really fishy email like company XYZ at I don't know what dot who on earth knows where, okay? Something like that. You notice that the sender was from a really fishy email ID and so on. You know, you start studying the problem. You gather spam emails, you study, you try to find out as a human being the difference. Okay. Then once you understood the problem, which takes a lot of time, not easy, and a lot of resource and a lot of hard work, it's not easy, you would want to write a detection algorithm. So you're going from this step to this step. So you're writing some rules and your program would flag emails as spam if a number of these patterns are true, right? Or detected or whatsoever. Okay, then you would test your program. So you would evaluate this program, right? And based on the evaluation, you would take some decisions on this program that you wrote. So is it good enough? Is it not good enough? And so on. So if you're happy, just call it a day. So you're ready, right? That's if you're happy. So in case of good performance. Now, in case you're unhappy with the results, you go back. Well, here, unhappy. So bad results. And you try to find the mistakes in your program, whether there's bugs or I don't know what. So, right? So you'd repeat this process multiple times until the program is ready. Okay? Now, of course, this program is totally untrivial, and your program, if you successfully made it here, and this is really relative, as somebody else would not be satisfied with such a program, you would have spent a lot of time, right? So your program will likely become a long list of some, I don't know, if-else statements, complex rules, very relative, and all complicated stuff, right? So it's pretty hard to maintain. In contrast, a machine learning algorithm would not take this approach. It would automatically learn from words as such and other phrases, and you wouldn't have to, have human interference. It would pretty much do a good job by its own, thanks to the sophisticated algorithms we have today. So if we were to do a similar flow chart, it will look something like this. So of course, you'd first want to study the problem, but not the same way as studying the problem as previously. No, it's more or less trying to clean the data, We'll talk about this in coming lectures. After studying the problem, you're going to have some sort of machine learning algorithm. So you would train the machine learning algorithm, right? And once you're done with that, you will evaluate according to some performance. Evaluate with respect to performance P, right? If you're happy if performance is or meets the minimum requirements, then we say that the ML algorithm is ready. And of course, before proceeding, we're training the ML algorithm using examples or experience or data, right? So through data, of course. And if you're unhappy, you'd go ahead and analyze your errors and repeat. So this is much easier and way faster. And why is that? Well, since you're giving data based on spam and not spam messages, the machine is able to understand that even though you didn't, specify let's say the for you statement as an if statement that says, oh, if I see an email with this for you, or if I see it multiple times, then I label it as spam. Well, let's say you did not feed it this particular phrase. Well, it turns out that some machine learning algorithms are so sophisticated that they're able to, by themselves, learn that for you is actually a spammy word, right? And that's because it has not really occurred a lot in emails that are not spam. So there's another side of the story. It's not just focusing on phrases that occur in spammy emails. No, it's also the phrases that do not appear in the emails that are not spam, right? Other areas where machine learning really manifests is for problems that are either too complex for traditional approaches or have no known or optimal algorithm to solve. For example, consider speech recognition. Now, speech recognition is a very complicated field by its own, and really problems over there occur. Let's say, you want to write a program that is capable of distinguishing the words 1 and 2, right? So recording, let's say I record myself saying 1 and record myself again saying 2. So I feed that to the machine and I take a look at, the sampled audio waveforms. And according to those waveforms, I, set some rules that distinguish me saying 1 from 2. So you might notice that the word 2 starts with a high pitch. So 2, I say 2, right? So once you try saying 2, the pitch starts high, and pitch in audio signal processing is a really known metric, right? And it's a very important one. Whereas 1 starts with a low pitch. So you could, hard code an algorithm that measures the high pitch at the start of the audio waveform, and if it's above some certain threshold, then you say that this is a 2, and if not, it's a 1. Obviously, this technique will not, if you manage to make it work for just 2 symbols, 1 and 2, or two numbers, 1 and 2, good for you. But this will not scale up to, let's say, 9 numbers, or 19 numbers, or 9,000 numbers, right? You can start imagining the degree of complexity of your program, right? So the best solution that we have nowadays is to write an algorithm that could learn by itself, given many example recordings for each word. So also do not forget that, going back to the 1-2 example, each and every person have different levels of pitches. So some other people might not have a high pitch when saying 2, right? But this is also person dependent. Well, machine learning algorithms will, let's say you want to teach it how to say or how to separate 1 from 2. You just feed it a lot of data, and the more diverse the better, from different kinds of vocals, and by itself it would be able to make some rules to separate different numbers. Now, we might get lost that machine learning is for machines and human beings have nothing to do with it, but that's not true. It could actually help us human beings learn a lot from the algorithms. The machine learning algorithms can be inspected to see what they have learned. For example, once the spam filter has been trained on enough spam, it can easily be inspected to reveal the list of words and combinations of words that it believes are the best predictors of spam, right? And sometimes this will reveal unsuspected correlations on new trends, therefore allowing us to form a better understanding of the model or the trend that is going on. Now, I don't know about you, but other applications of this, and this was 2 years ago, was the AlphaZero. And what this machine learning algorithm did was actually beat the world champion in chess after teaching itself in 4 hours. Look at that. It was designed and implemented by Google's AI sibling, DeepMind. And so the idea here is that not only could machines actually help us understand more about the model, it could actually understand the model way better than we do, and hence see patterns within the data that we could not. So all in all, problems for which existing solutions require a lot of hand tuning or a lot of complicated code, one machine algorithm could do the job way better and much faster. Also, machine learning algorithms are flexible, so they can adapt to new data. Let's say you arrive tomorrow with another batch of data, you can actually feed it this data, okay? So it is fast, flexible to data, and could teach us what we could have never known by ourselves, or it took us a lot of time to learn by ourselves. Okay, so there's many different types of machine learning methods that is useful to classify them into broad categories based on whether or not they are trained with human supervision. So in that case, we talk about supervised, unsupervised, semi-supervised, and even reinforcement learning. So let's talk a bit about that. So here we're classifying the methods based on human supervision. So we've got these 4 categories. So in supervised learning, the training data you feed to the algorithm includes the desired solutions. So you have the training data that you've got some sort of features with the data and their corresponding labels. So for example, the spam filter problem could be seen as a supervised learning 1. So you're classifying, you're putting into different classes. So the task of the method here is to put the new coming inputs into different bins or classes. So you're classifying the emails whether they're spam or not. Another typical task is to predict numeric values such as price of cars or the stocks. So usually when you're predicting, you're given a set of features such as mileage, age or brand, temperature, and many other features that are called predictors, right? So in supervised, this sort of task is referred to as regression. And to train the system, you need to give it many examples of cars. For example, if you're predicting a price of a car, along with their predictors such as price, age, price, brand, mileage, and many others, right? Now, let me introduce you to some well-known supervised algorithms that we'll be talking about. You've got KNN, or the K nearest neighbors, linear regression, SVM, or support vector machines, decision trees and random forests, and neural nets or neural networks, right? So those are the most popular, even though there's many others, and I'm sorry if I didn't mention other supervised machine learning algorithms, but those are the most, famous ones. Now in unsupervised learning, as the name suggests, the training data is unlabeled. So we do not know the response of the system, for example. We don't know if we give, for example, the set of spam emails or not, and we do not label them because we might not have the labels, or we might not know the labels or the response, right? So the output in this case is not known even in the training data. So here we leave the machine learning algorithm to figure out the response by itself. In this case, we say that the system tries to learn without a teacher, okay? And really, there's a lot of methods here as well, such as clustering methods that include k-means, HCA, and EM, expectation maximization. We've also got a class of methods known as visualization and dimensionality reduction methods, such as the well-known principal component analysis, PCA, followed by the kernel PCA, LLEs, also known as locally linear embedding methods, and the TSNE stands for T-distributed stochastic neighbor embedding. And last but not least, we've got association rule learning, such as a priori or a class. Let's say here you've got a certain blog, right? You've got a lot of data about visitors of your blog, and you're interested in a clustering algorithm that tries to detect groups of similar visitors. So say these are your visitors, this is the training set, and you're given some features. Let's say this is feature 2, and this is feature 1, okay? So again, you'd like to cluster those visitors according to some similarity between your visitors. So you come up with a clustering method that clusters those visitors in one cluster, those here in another one, right here, and over here. Okay? One important thing here is to know that you don't have labels on your visitors. You just have the features, age, gender, and so on. So let's say F1 stands for age, F2 stands for gender, and at no point you have a response. Don't have any label. That's what you're trying to figure out, right? So you can't just come and, give a training data with labels in this case, right? So here we say that this is an unsupervised problem, and you're most probably looking for an unsupervised method to cluster different visitors. For example, the HCA method will start by, roughly speaking, let's say 2 classes, and then within each class or cluster would also segregate the visitors into more classes. So you're forming a certain hierarchy in the data, right? And why is this useful? Well, you will start noticing some patterns in different visitors. Say you find out that 66% of your visitors are males who love comic books and would read your blog in the, let's say, in the morning, while let's say 10% are the youngsters who love just visiting your website during the weekend and so on. So that would help you target your posts better to dedicated audience. Now, visualization algorithms are also good examples of unsupervised learning algorithms, where the problem here is that you feed them a lot of complex and unlabeled data. Again, unlabeled, of course, because it's unsupervised, and they output a sort of 2D or 3D representation of your data that can easily be plotted in 2 or 3 dimensions. Now, these algorithms try to preserve as much structure as they can. For example, say you're trying to keep separate clusters in the input space from overlapping in the visualization, so that you can, better understand how the data is organized and perhaps identify some sort of hidden patterns. Somehow different but related task in visualization is dimensionality reduction, where the goal is to simplify the data. Let's say you've got n-dimensional data, really hard to analyze or decompose, or I don't know what the task is, but your goal here is to simplify the data as much as possible without losing information, without losing too much information. Now, one way to do this is to merge several correlated features into one. For example, a car's mileage highly correlated with its age. So the dimensionality reduction algorithm here would try to remove one feature and tell you to focus on the other, because there's redundance in your data. It tells you just forget about the mileage and, focus on the age of the car. If you know the age, you can tell, or you can have a good idea, or you can be confident about some sort of mileage range. Keep it that way. When you're doing this, you're actually doing feature extraction. You're extracting important features in the data that could tell you the response of the system. Yet another important unsupervised task is anomaly detection. For example, detecting unusual credit card transactions to prevent fraud. or catching manufacturing defects, or even automatically removing outliers from a data set before feeding it to another learning algorithm. Again, let's say you've got some unlabeled data with features 1 and 2, right? And you see that you've got the data with a sort of trend over here clustering around a certain line, right? So you see that there's some sort of normal deviation away from this line, for example, and you see this isolated data point over here. Now, this is usually referred to as an outlier or anomaly, okay? And what anomaly detection algorithms do is just tell you that be careful before training your data, just, remove these anomalies or outliers to get a good performance. Okay, forget about those data, they're just not normal. So the system is trained with normal instances, and when it sees a new instance, it can tell whether it looks like a normal one or an anomaly, right? So this is what visualization and dimensionality reduction algorithms tend to do in short. And last but not least, you've got association rules, in which the goal here is to explain large amounts of data and discover interesting hidden relations between attributes. For example, let's say you have a supermarket and you're running an association rule on your sales, and you find out that people that buy barbecue sauce and French fries will also tend to buy steak, right? Which makes sense, because who'd want to have a steak without fries, right? So you may want to place, in this case, these items close to each other because they are correlated in one way or another. In this case, we say that you're trying to associate rules with your learning method. Semi-supervised learning could be seen midway between unsupervised and supervised, because some algorithms can deal with partially labeled training data and the others are left out. So let's say you've got this training set over here. Some of them are labeled. Let's say this guy has a label, so does this guy, and let's say this guy, whereas the others are left unlabeled. For example, Google Photos, which is a photo hosting service, is a good example here. When you upload all your family photos to the service, it automatically recognizes that the same person A shows up in photos 6 and 12, while another person B shows up in photos 7, 9, and 11. This is the unsupervised part of the algorithm. It's clustering. Now, all the system needs is for you to tell it who these people are, right? So you just give it a label per person and it is able to do the work for you. It will tell you that this person appears in multiple photos, which is very useful when you want to search photos in the gallery that contain person A and person B. Google Photos is one very good service. Now, a note here is that most semi-supervised learning methods are a combination of unsupervised and supervised. For example, DBNs right here, which stands for deep belief networks, are based on unsupervised components that are called RBMs, that is restricted Boltzmann machines. They're stacked one on top of the other. That's how you form the DBN. Now, RBMs are trained sequentially in an unsupervised manner, and then the whole system is fine-tuned using supervised learning technique, okay? So the unsupervised counterpart over here is the RBM, and then you train each RBM with a supervised technique. Okay, that's it for a brief introduction on semi-supervised. Now, reinforcement learning is a very different approach. The learning system here, which is called an agent, can observe the environment, select and perform actions, and get rewards in return, also known as penalties in case of negative rewards. As if you've got a game and you're rewarding your agents with a reward or a penalty. Then it must learn by itself what is the best strategy. It's called a policy. And this term is really known in scheduling or game theory algorithms. So you've got a policy in which the agent is left to learn by itself given the positive or negative rewards, right? So back to the example here on the DeepMind system, the AlphaZero, which actually uses reinforcement learning. So in particular, AlphaGo program uses reinforcement learning. So it made the headlines, again, this was 2 years ago in 2017. So it learned its winning policy by analyzing millions of games and then playing many games against itself. Imagine a robot playing a machine playing against itself to improve its own performance. The learning was turned off during the games against the champion, so that, one might not say, oh, that machine cheated. It learned while it was competing. So AlphaGo was just applying the policy it had learned using previous experience. It had analyzed, again, millions of games. That's very interesting. Now, another way to classify machine learning methods is by seeing if the method could learn on the fly, how it could learn on the fly. I call it epsilon-Learning on the fly. So it would learn incrementally as the method is being applied. So two major classes of methods are to be dealt with over here. First one is termed batch learning. In batch learning, the system is not capable of learning by itself. It must be trained using all the available data, the training data. Now this will take a lot of time and computing resources that is done offline. So batch learning is also referred to as offline learning. The system is first trained and then it is launched into production and runs without any more learning. Just applies what it has learned and that's it. Now that's not 100% correct, because in case you want a batch learning system to know about new coming data, you need to train a new version of the system from scratch on the previous data plus the new arrived data. So you give it the total data set again to train it, right? And that is very exhaustive, because why would I want to learn everything again from scratch, right? I already learned the previous data set. So let's say I trained this system using, 1,000 samples. And then today, 100 samples arrived. Why on earth would I want to feed my algorithm 1,100 samples, whereas I already did the exhaustive job and fed it 1,000 samples over here? Why would I want to repeat this? So that's where online learning comes into play. So in online learning, you train the system by feeding it data points sequentially. This is way cheaper than batch learning. This way, if you already fed it 1,000 samples, you can come again tomorrow without any, modification on the training set, without appending those 100 samples, and just feed it the 100 samples directly on top of the 1,000 that it has already learned, right? So in this case, you'd refer to training sets as batches or mini batches. So you've got the first mini batch, the second mini batch, and so on. So you're feeding it batches of data, okay? So why is this useful? Because first of all, it's fast, and second, it's cheap. Learning from small batches is way cheaper than, learning all this at once. So we say that the system can learn on the fly. This is useful for systems that receive data as a continuous flow. For example, stock prices. You've taught your model using the 1,000 days that have passed, right? You're updating your data set every day. And let's say you reach a day over here, let's say 1,000 days have passed, and the system has learned using 1,000 data points. You don't want to come again every day and train it 1,001, 1,002, and so on. No. The data by nature is coming in as a continuous flow, and thus the need to adapt to change autonomously. It is also a good option if you have limited computing resources. Once an online learning system has learned about new data instances, it does not need them anymore. So you can just discard them and continue with the learning process. This could save a lot of memory space, for example. Another important parameter of online learning systems is how fast they could adapt to changing data. This is called the learning rate. If you have a high learning rate, the higher this is, the more your system will adapt to new coming data. But it will also tend to forget the old data, okay? There's a compromise here. That said, you don't want a spam filter to flag only the latest kinds of spam it was shown. On the other hand, if your learning rate is low, the system will have more inertia. What does that mean? It means it will learn more slowly, but it will also be less sensitive to noise in the new data or to sequences in the new data point. Okay, so this parameter has to be chosen with care. The challenge here is that if bad data is fed to the system's performance will gradually decline. If we are talking about a live system, your clients will notice. For example, bad data could come from a malfunctioning sensor on a robot. Let's say a robot is equipped with 4 antennas and one is not working. And you're running an online learning algorithm, then we'll start accumulating error. And suddenly the online machine learning method will start to perform very bad. So in these cases, human interference is usually used to monitor the system and see if the system is learning correctly or not. Okay? That's the other side of it. And the last way to categorize your methods is instance versus model-based learning. So what do we mean by that? Now, in instance-based learning, the models are learning by heart. So if you were to create a spam filter this way, it would just, flag all emails that are identical to emails that have already been flagged by users. Not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam filters, your spam filter could be programmed to also flag emails that are very similar to known spam emails. This requires a measure of similarity between two emails. A very basic similarity measure between emails could be to count the number of words they have in common. If two emails have the same number of words, we say that they're exactly the same. And as the number of words diverges, the more unsimilar they start looking. Now, this approach is called an instance-based learning, where the system learns examples by heart, then generalizes to new cases using a similarity measure. Whereas model-based learning builds a model of these examples, then uses that model to make predictions. For instance, suppose you want to know if money makes people happy. So you download the Better Life Index data from the OECD's website. So here's the data. And here you've got a massively enormous data set, a lot of features. You see that per country, see that we have a feature over here that has to do with life satisfaction, right? So you get a life satisfaction score per country over here. It's this column over here. And you also go and visit the IMF. And over here, it gives you the GDP per capita of the countries, okay? So you decide to concatenate per country the GDP in USD and the life satisfaction from the OECD. And you decide to do a study to see if money makes people happy. And if we were to look at the plots on a 2D axis, this is what you get. So here we're plotting life satisfaction versus GDP per capita. In a model-based approach, there seems to be a trend over here, right? So we can fit more or less a line over here. If we do some regression analysis, maybe this is what we can say. Although there's some noise, it looks like satisfaction goes up linearly as the country's GDP per capita increases. So you might decide to model life satisfaction as a linear function of GDP per capita. This actually is called model selection. So you selected a linear model of life satisfaction with just one attribute, the GDP per capita. This is one way, okay? It could definitely turn out to be wrong, right? Because there's no genie around telling you that this is a linear model. It's your instinct. You came up and said, this is a linear model. Once you do this, you have selected a model. And this is a model-based learning method. So here you come, you say, oh, okay, I'll model life satisfaction as some intercept plus a slope multiplied by the GDP, right? This is K to index stuff, okay? So right here you'd have two model parameters, beta 0 and beta 1. And, by tweaking these parameters, you can make your model represent any linear function, okay? It could turn out to look like this, or maybe this, or this. So according to the choice of beta 0 and beta 1, your line will look different. And so here comes the question, what are the beta 0 and beta 1 that best approximate the model if you took the linear approach. Now, how can you also know which values will make your model perform best for new coming data? For this, we need the performance that we talked about over here. So we need a certain performance to judge the goodness of the model. You could define a utility function or fitness function that measures how good your model is. Or you can just define a cost function that measures how bad it is. For linear regression problems, and this is what we just did over here, we typically use a cost function that measures the distance, the Euclidean distance between the linear model's prediction and the training examples. The objective is to minimize this distance. So in linear regression, you feed it your training examples and it finds the parameters that makes the linear model fit best to your data. This is called training the model. In our particular case, the algorithm finds that the optimal parameters, in case you used linear regression, you will come up with values that, over here, we'll see that this beta 0 over here is somewhere around 4.85, and the beta 1, which is the slope, is somewhere around 4.91 times 10 to the power minus 5. Something like that. So in other words, what linear regression does, and we'll be talking about this in details, is find a linear function that fits the data, such as the total error or residuals, called residuals over here, are minimized. Okay? After you do that, then given an unseen GDP, let's say there's a GDP that is not included in the data set, you can predict life satisfaction. Okay, so in short, this is how machine learning methods categorize, whether by human supervision or by learning on the fly, or even according to instance versus model-based learning method. Now, let's take a step ahead and see what could go wrong. Now, in machine learning, your task would probably be to select a learning algorithm and train it on some data. See if the algorithm works bad, or just maybe you gave it the wrong data. We say that the examples are bad. So one challenge in machine learning is insufficient quantity of training data. Now, one example here is, imagine you've got a kid and you're teaching the kid to recognize an apple. You just point at an apple and say, this is an apple. Probably you'd repeat that multiple times, and voila, that's it. The child learned the apple from the banana. Machine learning is not there yet. It takes a lot of data for most algorithms to work properly. And by a lot, we mean a lot. Even for very simple problems, you typically need thousands of examples. And for complex problems such as image or speech recognition, you may need millions of examples. I'm not kidding. You need a lot of examples when it comes to computer vision, image processing, there's a paper all these kind of stuff on this particular topic by Microsoft researchers Michel Banco and Eric Brill in 2001. This is a very famous paper scaling to very, very large corpora for natural language disambiguation. Now, Banco and Brill show that very different machine learning algorithms, including fairly simple ones, performed almost identically well on a complex problem of natural language disambiguation. Now, in case you don't know what this is, imagine you've got homophones, so 8 and the number 8, right? Or 2 and number 2, okay? So this is called natural language disambiguation. Showed that different machine learning algorithms, and by different we mean very different. We scroll down here, we've got naive Bayes, perceptron, winnow, and memory based. So those are really different, and they're performing identically well on such a complex problem, that is natural language disambiguation. But this only happens given enough data. So look here, we're giving them 1 million, 10 million, 100 million words so that they perform almost the same. And I quote, the authors say that these results suggest that we may want to reconsider the trade-off between spending time and money on algorithm versus development versus spending it on corpus development. So over here, it's algorithm versus data. That's the point here. The idea is that data matters more than algorithms nowadays. So the more data you have, the more powerful the algorithm could perform. So as we saw over here, many different algorithms performed equally well. Now, there's another paper by Google. This paper is very interesting. I urge you to skim through it at the least. And if you have the time, just read it carefully. This paper is very popular and it was published in 2019 by Alon Halevy, Peter Norvig, and Fernando Pereira. It's entitled The Unreasonable Effectiveness of Data. And in this paper, they show how data matters more than algorithms for certain complex problems. So here's a nice phrase that really got to me that says the same meaning can be expressed in many different ways. And the same expression can express many different meanings. So the paper is all about information and data sets. Another challenge over here is non-representative training data. And by that, we mean the sensibility of the training data with respect to new arriving cases. So in order to generalize well, it is very important that your training data represents the new cases you want to generalize to. This is true in particular when you use instance-based learning or model-based learning. For example, let's say the set of countries we used earlier over here were not actually perfectly representative. A few countries were, let's say, missing. Let's say I've got, I don't know, the green point, Luxembourg, which is down here. It's far away, but it's down here. Let's say Switzerland is this country, okay? And this is another way to see why data is important. Well, if you run linear regression again, the line would push the slope downwards, right? So in that case, your linear regression would give you something like this. In that case, you have improperly represented your data because newly arriving points would be predicted using a wrong slope. So as you can see, not only does one data point alter the line, but it makes it clear that such a simple linear model is probably never going to work well, right? And actually, this is a real data point. Actually, Switzerland is somewhere close to 80,000. And Swiss people are less happy than people in Brazil. Brazil is way down here, low GDP, and Switzerland, high GDP, but lower life satisfaction. So it is not true that very rich countries are happier than moderately rich countries. And conversely, it seems that some poor countries seem to be happier than many rich countries. Now, by using a non-representative training set, such as the one we used over here, I'll cut Switzerland out, such as the one we used over here, we trained a model that is unlikely to make accurate predictions, right? Especially for extreme cases, the very rich and very poor countries. Now, keep in mind that it is crucial to use a training set that is both rich and representative of cases you want to generalize to. This is often harder than it sounds, right? If the sample is too small, you will have sampling noise, right? Even large samples can be non-representative if the sampling method is flawed. This is called now a famous example bias. On sampling bias is probably during the US presidential election in 1936. It is so famous that Wikipedia has a page for it. Over here, we see that Roosevelt was competing, Landon. See that Roosevelt scored actually the double, almost the double as Landon. And a very well-known magazine by the name of The Literary Digest, they conducted a very large poll, sending mail to about 10 million people. It got around 2.27 million answers and predicted with high confidence that Landon would get 57% of the vote. Instead, Roosevelt won with 62% of the votes. The flaw here was with Literary Digest sampling method. Now first, to obtain the addresses to send the polls to, the Literary Digest used telephone directories, lists of magazine subscribers, and club membership lists, and the like. All of these lists tend to favor wealthier people who are more likely to vote Republican. So hence Landon, because Landon was a Republican, hence favored by the rich. Second, by ruling out people who don't care much about politics, the literary digest, and other key groups. This is a special type of sampling bias called non-response bias. When you rule out people that just, don't care. That actually has a name in statistics. Anyways, here is another example. When talking about sampling bias, this is a very important event that happened where sampling bias comes in play. Now, another challenge in machine learning is poor quality data. So as you can see here, we're focusing a lot on data because that's what you're feeding the algorithm. And algorithms feed on data where we feed on food. Anyways, when we say poor quality data, we mean that you're training data that is full of errors, outliers, a lot of noise, which will typically make it harder for the system to detect patterns and hence will perform very bad. And this is where cleaning up your training data comes in play. Truth be told, most data scientists spend a significant part of their time just cleaning the data. For example, if some instances are clearly outliers, it may help to simply discard them or try to fix the errors manually. And if some instances are missing a few features, let's say 5% of your customers did not, specify their age because they were too shy to say their age, or they just didn't give you an accurate number, or you just forgot to ask them, you must decide whether you want to ignore this attribute altogether, ignore these instances, or, fill in the missing data using some sort of interpolation method or something of that sort. Or maybe train one model with the features and one model without it, and so on. So many stuff data scientists do here to robustify the data against missing or noisy or whatever anomaly contained in the data. Another challenge that we could talk about is irrelevant features. Now there's a saying here that says garbage in, garbage out. Your system will only be capable of learning if the training data contains enough relevant features and not too many irrelevant ones. Now, I know many machine learning algorithms will automatically figure out which features are more important and worthy highlighting on, whereas others are just nonsense or just random with respect to the predictors. So that brings us to a critical part of success of a machine learning method, which is coming up with a good set of features to train on or to feast on. This process is called feature engineering, and it involves feature selection, feature extraction, and creating new features by gathering new data. Now imagine that you're studying the sales of ice cream in a certain country and you're given features such as the weather, temperature, humidity, and so on. And one feature is something totally unrelated. It's the outcome of votes in 1936. Now, as you can see, this feature has nothing to do with sales of ice cream. So this feature is totally irrelevant. So better not to have it. And that's one involvement of feature engineering. Now that we talked about challenges involving the data, let's see examples of bad algorithms. So one instance of that is, now overfitting is one way of, let's say, overgeneralizing a certain concept. Say you're visiting a foreign country and the taxi driver just, rips you off. At least that's what happens in, I don't want to mention the country, but whatever. You might be tempted to say that all taxi drivers in that particular country are thieves, whereas that's not the case. Overgeneralizing is something that we humans tend to do, and unfortunately machines can fall into the same trap if we are not careful enough. In machine learning, this is called overfitting, and it means that the model performs well on the training data, but it does not seem to generalize well enough. For example, back to the life satisfaction versus GDP capita example. Let's say we did not pick a linear model. We instead picked a higher degree, a polynomial interpolation 1. Even though we see good performance over here on the training data and even better than the linear model, would you really trust this region over here and over here? I mean, this is it's fluctuating a lot, and it's actually going to negative values between 60,000 and somewhere around 70,000. So this phenomenon is known as overfitting. And complex models such as deep neural networks can detect subtle patterns in the data. If the training set is too noisy or too small, which introduces the so-called sampling noise, then the model is likely to detect patterns in the noise itself. So we're saying it's overdoing the job, it's overfitting or overgeneralizing. It's thinking too much. It's looking at the noise as if there were patterns in the noise. Of course, that happens for a high variance on the noise or for a small data set. Now, back to this problem over here. Let's say we've got more features. Let's say we're feeding the model with, you're feeding life satisfaction with more features or more attributes, including uninformative ones such as the country's name, which clearly the life satisfaction doesn't care about, right? It doesn't care whether it's France or Brazil or Switzerland. It doesn't care. It just needs a number, right? In that case, a complex model may detect patterns like the fact that all countries in the training set that contain W in their names, such as New Zealand, that is over here, or Norway, or Sweden, or even Switzerland, that's right over here, they might have some sort of pattern within them. Now, how confident are you that the W satisfaction rule generalizes to Rwanda or even Zimbabwe, which are over here somewhere, right? Obviously, this pattern occurred in the training data is by pure coincidence. But the model has no way to tell whether a pattern is real or just simply noise in the data. It is worth to keep in mind that overfitting happens when, so long story short, we can talk about days on overfitting, but long story short, overfitting happens when the model is too complex relative to the amount and the noisiness of the training data. Possible solutions here are to either gather more training data, so reduce the sampling noise, or reduce the noise within the training data, fix some, that is, for example, fix data errors and possibly filter out outliers, or you try to simplify the model by selecting, fewer parameters. For example, you select a linear model here instead of a fancy polynomial interpolation, fancy interpolation model, because really sometimes linear model does a really good job. Now, simplifying a complex model actually has a term, and it's called regularization. You probably heard of it, probably in linear algebra or convex optimization, I don't know what, but in machine learning, it has a different explanation. It's when you're trying to make a complex model be more regular, be more simplified. Now, if we go back to the linear model where LS is beta 0 plus beta 1 times GDP, here we say that the learning algorithm has 2 degrees of freedom due to beta 0 and beta 1, because that's what it's trying to learn, right? The model will try to adapt the training data and try as much as it could to tweak beta 0 and beta 1 to satisfy everyone. That is all the data within the training set. If we forced that theta 1, or we constrain that beta 1 is 0, if we perform linear regression, given that beta 1 is 0, the algorithm would only have 1 degrees of freedom and would have a much harder time fitting the data properly. All it could do is move the line up or down, because beta 1 is a slope, and when you come and force it to be 0, what other choices do you have? It's just a vertical line and you're trying to adjust, right? You're trying to push it upwards or downwards. That's what linear regression would do in that case, right? So in the end, it will end up somewhere around the mean of the data. It would sit on the mean of the data, right? Now, this is a very simple model indeed, but it is highly inaccurate. Now, another way around this is that if we allow the algorithm to modify beta 1 without making it explode to large values, that is, we'd constrain the value of beta 1 to be below some certain value, let's say t, a threshold, then the learning algorithm will effectively have somewhere in between 1 and 2 degrees of freedom. It's not 1 and it's not 2. It's somewhere in between, right? Because we're constraining the model We don't want to apply pure linear regression. No, we're applying linear regression, but subject to this constraint. Now, this indeed will produce a simpler model than with 2 absolute degrees of freedom, but more complex than just 1. You want to find the right balance between fitting the data perfectly and keeping the model simple enough to ensure that it will generalize well. Now, we'll be talking about overfitting a lot within this course, and just keep this problem in mind. Another one is the other extreme, that is underfitting. And this is the total opposite of overfitting, and it occurs when your model is too simple to learn the underlying structure and patterns of the data. For instance, a linear model of life satisfaction versus GDP is prone to underfit. Reality is just way more complex than any polynomial or linear model or whatsoever equation you just put over, or whatever simple equation you just put over there with some fancy powers and stuff like that. Reality is way more complex, and so predictions are bound thus to be inaccurate, even on the training examples that you fed. The main fix here is selecting a more powerful model, obviously, and feeding better features to the learning algorithm. And of course, reducing the constraints on the model itself. So by now, you probably learned a lot about machine learning. No, I'm just kidding. We just talked about basics. It's okay if there's a lot of concepts that are not clear, such as examples, training data. I'm just introducing you to some terms over here. Okay. So it's good to keep in mind how we categorize the data, whether supervised, unsupervised, semi or reinforcement, whether it's batch versus online learning, instance versus model-based learning, and the challenges, where we talked about challenges in the data set itself, whether it being non-representative, insufficient in quantity, poor, or even irrelevant. And we talked about challenges within the algorithm itself, whether it's over or underfitting the data. Now, one last topic I'd like to talk about before calling this lecture a day is testing and validating. Now, the only way to know how well of a model you have or how well it will generalize to new cases is to actually try it out on the cases you have. Let's say you've got this training data set over here and the OECD data set with the following features over here for a country, and you did your study, you're happy, you got a model. Well, gotta test it for saying the model is ready. Well, one way of testing is to split your data set into training. Say a rule of thumb is 80%, so you pick 80%, let's say, be your training set, say the shaded regions over here. Let's say the rows corresponding to the shaded region, and the rest, the other 20%, corresponding to the test set, 20% for test. And your goal here would be to study the error rate on new cases. So you will train the model using the 80% that you picked, and you will pretend that these data points are newly arriving data sets, and you'll study the performance on these new points. If the training error is low, but the generalization error is high, it means that your model is overfitting the training data. So your model has dig really deep into the training data. Okay, so evaluating a model is simple enough. Just use a test set. This will open doors to new questions. So let's say you're hesitating whether the model should be linear or polynomial. Well, this is a good time to figure out. How can you decide? Well, one way is to train your data on both models and see which one performs better on the testing set. So let's say the linear model generalized better, but you want to apply some regularization to avoid overfitting. The question here is, how do you choose the value of the regularization hyperparameter, which we will be talking about in future lectures? Well, one option is to train on, let's say, 10 different hyperparameter values and find the one that minimizes the testing error. So let's say you come up with a model, you're ready to launch for production, but unfortunately it does not perform well in production. What just happened? Well, this means that you tuned your parameter too much that it only performs good for this particular testing set, so that it doesn't perform good on any other testing set. A common solution here is to have a second set called the validation set. So you train multiple models with various hyperparameters using the training set. You select the model and hyperparameters that perform best on the validation set. And when you're happy with that model, you run a single final test against the test set to get an estimate of the generalization error. Now, to avoid too much training in validation sets, a common practice here is to use cross validation. That is, the training set is further decomposed into complementary subsets. So let's say this is the first subset, this is the second subset, third one, and so on, right? Each model is trained against a different combination of these subsets and validated against the remaining parts. Once the model type and hyperparameters have been selected, a final model is trained using these hyperparameters on the full training set, and thus the generalization error is measured on the test set. Now, a popular paper here is the no free lunch theorems for optimization by Wolpert and Macready, where they demonstrate that if you make absolutely no assumption about the data, then there is no reason to prefer one model over any other. This is called the no free lunch theorem, as stated here. And actually, in this paper, they derive multiple NFL theorems. This is popular in so-called black box optimization algorithms, where the function you're trying to optimize is unknown, thus the name black box. So what they demonstrate is that if you make no assumption about the data, then there is no reason to prefer one model over any other. For some data sets, the best model is just a linear model, while for others it is a neural network. There is no model that is guaranteed to work better, hence the name of the theorem, no free lunch. The only way to know for sure which model is best is to evaluate them all. Now, since this is not practical, neither achievable, in practice, you make some reasonable assumptions about the data and you evaluate only a few reasonable models. For instance, for simple tasks, you may just want to evaluate linear models with various levels of regularization. And for complex ones, you may want to evaluate various neural networks. Okay? This paper is really sophisticated, contains a lot of high-level math. If you have the time, you can go ahead and dig deep into it. To be honest, I've made it down till here, and the rest I have no clue what it says. I should get back to reading it one day. So that's it for this lecture, where I hope I did a good job at introducing you to machine learning, showing you the different and useful motivations of machine learning, describing what it is, the different types of machine learning, the challenges in machine learning and what could go wrong, whether it's in the data set or the algorithm itself. And finally, we talked a bit about testing and validation. Of course, we're going to dig deeper into those topics in future lectures and see how to implement each and every one of those algorithms using TensorFlow and Scikit-learn. Thanks for watching. If you enjoyed this lecture, please consider subscribing to my channel, liking this video, sharing it on social media. And if you have any questions whatsoever, just leave a comment down in the comment section below. I'll make sure I'll get to it as soon as possible. Thank you so much, and I'll see you in future lectures.